Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 9, Geometric Constructions, Invariants. Section 85, Improper Elements, Proposition K2. We have called attention frequently to the fact that the nature of the field of points on a line is not completely determined by assumptions A, E, P under which we are working. We have seen in particular that this field may be finite or infinite. The example of an analytic space discussed in the introduction shows that the theory thus far developed applies equally well whether we assume the field of points on a line to consist of all the ordinary rational numbers, or of all ordinary real numbers, or of all ordinary complex numbers. According to which of these cases we assume, our space may be said to be the ordinary rational space, or the ordinary real space, or the ordinary complex space. Now, in the latter, we know that every number has a square root. Moreover, each of the former spaces, the rational and the real, are clearly contained in the complex space as subspaces. Suppose now that our space S is one in which not every number has a square root. In such a case, it is often convenient to be able to think of our space S as forming a subspace in a more extensive space S prime, in which some or all of these numbers do have square roots. We have seen that the ordinary rational or ordinary real spaces are such that they may be regarded as subspaces of a more extensive space in the number system associated with which the square root of any number always exists. In fact, they may be regarded as subspaces of the ordinary complex space, which has this property. For a general field, it is easy to prove that if a sub 1, a sub 2, a sub n are any finite set of elements of a field F, there exists a field F prime containing all the elements of F such that each of the elements a sub 1, a sub 2, a sub n is a square root in F prime. This is, of course, less general than the theorem that a field F prime exists in which every element of F is a square. But it is sufficiently general for many geometric purposes. In the presence of assumptions A, E, P, H0, it is equivalent, chiefly section 54, to the following statement. Proposition K2. If any finite number of involutions are given in a space S satisfying assumptions A, E, P, there exists a space S prime of which S is a subspace, such that all the given involutions have double points in S prime. Footnote: we use the word subspace to mean any space, every point of which is a point of the space of which it is a subspace. With this understanding, the subspace may be identical with the space of which it is a subspace. The ordinary complex space then satisfies proposition K2. A proof of this theorem will be found at the end of the chapter. The proposition is, from the analytic point of view, that the domain of rationality determined by a quadratic problem may be extended so as to include solutions of that problem. The space S prime may be called an extended space. The elements of S may be called proper elements, and those of S prime which are not in S may be called improper. A projective transformation which changes every proper element into a proper element is likewise a proper transformation. One which transforms proper elements into improper elements, on the other hand, is called an improper transformation. Taking proposition K2 for the present as an assumption like A, E, P, and H0, and noting that it is consistent with these other assumptions because they are all satisfied by the ordinary complex space, we proceed to derive some of its consequences. Theorem 1. A proper one-dimensional projectivity without proper double elements may always be regarded in an extended space as having two improper double elements. Assumptions A, E, P, H0, and K2. Chiefly exercise, page 261. Proof: suppose the projectivity given on a conic. If the involution which belongs to this projectivity had two proper double points, they would be the intersections of the axis of the projectivity with the conic. and hence the given projectivity would have proper double points. Let S prime be the extended space in which K2, the involution, has double points. There are then 2 points of S prime in which the axis of the projectivity meets the conic, and these are, by Theorem 20, Chapter 8, the double points of the given projectivity. Corollary 1. If a line does not meet a conic in proper points, it may be regarded in an extended space as meeting it in 2 proper points. Assumptions A, E, P, H0, K2. Corollary 2. Every quadratic equation with proper coefficients has 2 roots which, if distinct, are both proper or both improper. Assumptions A, E, P, H0, K2. For the double points of any projectivity, satisfy an equation of the form cx squared plus the quantity d minus a times x minus b equals 0. Theorem 11, Corollary 4, Chapter 6, and any quadratic equation may be put into this form. Theorem 2, any 2 involutions in the same one-dimensional form have a conjugate pair in common, which may be proper or improper. Assumptions A, E, P, H0, K2. This follows at once from the preceding and Theorem 23, Chapter 8. Corollary. In any involution there exists a conjugate pair, proper or improper, which is harmonic with any given conjugate pair. Assumptions A, E, P, H0, K2. For the involution which has the given pair for double elements has, by the theorem, a pair, proper or improper, in common with the given involution. The latter pair satisfies the condition of the theorem. Theorem 27, Corollary 1, Chapter 4. We have seen earlier, Theorem 4, Corollary, Chapter 8, that any 2 involutions with double points are conjugate. Under proposition K2, we may remove the restriction and say that any 2 involutions are conjugate in an extended space dependent on the 2 involutions. If the involutions are on coplanar lines, we have the following. Theorem 3. 2 involutions on distinct lines in the same plane are perspective, the center of perspectivity being proper or improper, provided the point of intersection of the lines is a double point for both or for neither of the involutions. Assumptions A, E, P, K2. Proof. If the point of intersection O of the 2 lines be a double point of each of the involutions, let Q and R be an arbitrary pair of one involution, and Q' and R' an arbitrary pair of the other involution. The point of intersection of the lines Q, Q', and R, R' is then a center of a perspectivity which transforms elements which determine the first involution into elements which determine the second. If the point O is a double point of neither of the 2 involutions, let M be a double point of one and M' of the other. These double points are proper, or else exist in an extended space S', which exists by proposition K2. Also, let N and N' be the conjugates of O in the 2 involutions. Then, by the same argument as before, the point of intersection of the lines MM' and N' may be taken as the center of the perspectivity. It was proved in section 66, chapter 7, that the equation of any point conic is of the form, equation 1, a11 x1 squared plus a22 x2 squared plus a33 x3 squared plus 2a12 x1 x2 plus 2a13 x1 x3 plus 2a23 x2 x3 equals 0. But it was not shown that every equation of this form represents a conic. The line x1 equals 0 contains the point 0, x2, x3, satisfying equation 1, provided the ratio x2 to x3 satisfies the quadratic equation a22 x2 squared plus 2a23 x2 x3 plus a33 x3 squared equals 0. Similarly, the lines x2 equals 0 and x3 equals 0 contains points of the locus defined by equation 1, provided 2 other quadratic equations are satisfied. By proposition K2, there exists an extended space in which these three quadratic equations are solvable. Hence, equation 1 is satisfied by the coordinates of at least two distinct points, P, Q, proper or improper. Footnote: proposition K2 has been used merely to establish the existence of points satisfying equation 1. In case there are proper points satisfying equation 1, the whole argument can be made without K2. A linear transformation, equations 2, rho x1 prime equal b11 x1 plus b12 x2 plus b13 x3. Rho x2 prime equals b21 x1 plus b22 x2 plus b23 x3. Rho x3 prime equals b31 x1 plus b32 x2 plus b33 x3 evidently transforms the points satisfying equation 1 into points satisfying another equation of the second degree. If, then, equation 2 is so chosen as to transform P and Q into the points 0, 0, 1 and 0, 1, 0, respectively, equation 1 will be transformed into an equation which is satisfied by the latter pair of points, and which is therefore of the form equation 3. A x1 squared plus c1 x2 x3 plus c2 x1 x3 plus c3 x1 x2 equals 0. If c1 is equal to 0, the points satisfying equation 3 lie on the two lines x1 equals 0, ax1 plus c2 x3 plus c3 x2 equals 0. And hence equation 1 is satisfied by the points on the lines into which these lines are transformed by the inverse of equation 2. If c1 is not equal to 0, the transformation, equations 4, x1 equal to x1 prime, x2 equal to negative c2 divided by c1 times x1 prime plus x2 prime, x3 equal to x3 prime, transforms the points x1, x2, x3 satisfying equation 3 into points x1 prime, x2 prime, x3 prime satisfying equation 5. The quantity A minus c2, c3 divided by c1, x1 prime squared, plus the quantity c1, x3 prime plus c3, x1 prime, x2 prime equals 0. But equation 5 is in the form which was proved in Theorem 7, Chapter 7, to be the equation of a conic, as the points which satisfy equation 5 are transformed by the inverse of the product of the collineations, equation 2 and equation 4, into points which satisfy equation 1. We see that in all cases, equation 1 represents a point conic, proper or improper, degenerate or non-degenerate. This gives rise to the two following dual theorems. Theorem 4. Every equation of the form a11 x1 squared plus a22 x2 squared plus a33 x3 squared plus 2a12 x1 x2 plus 2a13 x1 x3 plus 2a23 x2 x3 equals 0. Represents a point conic, proper or improper, which may, however, degenerate. And conversely, every point conic may be represented by an equation of this form. Assumptions A, E, P, H0, K2. Theorem 4 prime. Every equation of the form A11 U1 squared plus A22 U2 squared plus A33 U3 squared plus 2A12 U1 U2 plus 2A13 U1 U3 plus 2A23 U2 U3 equals 0 represents a line conic, proper or improper, which may, however, degenerate, and conversely, every line conic may be represented by an equation of this form. Assumptions A, E, P, H0, K2.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.